Hello everyone, it's Anu again, back again with another chemical engineering tutorial, and today we're talking about thermodynamic properties. So this is UHSG. If you've ever seen these and ever wondered what exactly is it or when to use it, this is the video for you. So let's get right into it. Now, I will assume that you have watched the energy balance course. If you haven't, I'll put a card up right now. You should watch that first so that you're comfortable and know what it is and what the terms are in there. I'll write it down right now so that you can see it. So we have du dt is equal to Q, which is our heat, shaft work, plus our inlet stream energies, minus our outlet stream energies, subtract the change in kinetic energy, subtract the change in potential energy. And so this is the total energy balance, right? Now we already see in this energy balance U, H, and so forth, right? So the question is, what exactly are these terms? So let's start with the most important one, which is U. Basically, this answers what is energy. U is the internal energy of a system. So if you were to take up all the energy in a system, right, the kinetic energy of molecules flying around, potential energy that you have in bonds or from height, etc., right? If you took up all of those individual types of energy, electrical, chemical, so forth, and you were to sum it up, you'd get the internal energy of a system. Now, the first law tells us that energy can't be created or destroyed. It can only move from one place to another, which is where we get ultimately, our energy balance, right? So our total energy balance is du dt is equal to everything here on the right-hand side. But let's say we have a closed system here. This is kind of a review from our energy balance part. But let's say we have a closed system, so there's no mass flowing in or out. Then our equation simplifies to du dt equals Q plus shaft work. Or if we're looking at a time course, delta U equals Q plus W. So obviously U is most easy to use when you have a constant volume, like a rigid closed system like I showed you here, right? So there's no movement, there's no expansion or contraction, there's no flow going on. So we only really care about the heat we put in and any shaft work that's being done, right? But of course, not every process is like that. We have reactors, distillation columns, heat exchangers that might not be rigid. Most of them are, but some of them are rigid. But they're also, more importantly, they're open systems, meaning you have things flowing in and out. So now that we have flow, we also have to account for the flow work, which is why we use H. So H, or the enthalpy of the system, accounts for both U, the internal energy, as well as the flow work that you do, right? So, I mean, if you go back to our energy balance, I'll scroll back up. We have du dt, not dH dt, right? But then we have our flow terms over here that contain the H term. So why? Because enthalpy only shows up when mass is crossing a boundary. So now let's take a look at an open system. Suppose we have an open system here. We have flow coming in and out. And so let's say you have fluid moving in. It doesn't just bring its own internal energy. It also has to do some work to push itself through the inlet against whatever the pressure is. That's the PV work. So it's doing some work, flow work, in order to actually move the fluid from out of the system into the system. And so that's the PV term. So the total energy that the fluid brings into the system is not just its internal energy, but also the flow work, PV, which is where we get our equation H equals U plus PV, which is why H appears in that flow term of the energy balance, as we saw before, these flow terms, and not in the overall energy balance. So every unit of mass crossing the system carries its internal energy plus the flow work. So it carries H worth of energy, stored internal energy plus the flow work. Now, if we were to put this in terms of deltas, right? So you have delta H equals delta U plus delta R to PV. There's a very famous example that we use where pressure is constant. So at constant pressure, we can take the pressure term out, and we get delta H equals delta U plus P delta V. And this is the common expression of enthalpy that you'll actually see. The change in enthalpy is equal to the change in the internal energy between inlet and outlet, plus the pressure times the change in the volume. So the enthalpy change becomes the actual energy change that happens to the fluid coming in and out. And so what's nice is that you can actually look up these values, right? So for example, let me actually make this example a little bit more concrete for you here. Suppose we have steam coming in 300 degrees Celsius, 1 megapascal, and it's entering a heat exchanger. And then once it comes out, it is a saturated liquid. And of course, it's still at the same pressure. We're going to use a constant pressure example. Well, you can actually look up what is the enthalpy coming in, what's the enthalpy coming out, and then you could actually find delta H by doing H out minus H in. You don't actually have to calculate the flow work because it's already embedded in the enthalpy values that you can search up using Perry's or um, NIST or whatever your preferred search engine is here. So that's H. Now, energy only answers one part of the question, right? U and H will tell you where energy goes, but it doesn't tell you whether it'll actually happen, right? So suppose I have a system like this, and there's a coffee cup in the middle of the system, and it's very hot. So I could have all the heat energy in the coffee cup and then a very cold room, or I can have energy from the coffee cup disperses over time and then it just goes, it's spread out throughout the system. And so the question then becomes, both of these cases, since the system is the entire room, U and H are basically the same. So the total energy of the system, which is U, or if there's anything flowing in and out, like maybe we're doing air changes or something, the H, they're not really changing. So even though the energy state is the same, the distribution of energy throughout the system is different. And that's where we use the entropy, S. So S is the entropy. And this is a measure of the molecular disorder. Now, the second law of thermodynamics tells us that the isolated system wants to increase the entropy, right? So the change in the entropy of an isolated system will either increase or stay the same. It never just decreases spontaneously. We can force it to decrease, of course, but it's not going to just do that spontaneously. The universe is always trending towards more disorder. So mathematically, we actually express this in a differential term, which is ds equals partial q over t. So in other words, if I add more heat at a lower temperature, I produce more entropy change, which matches the intuition, right? If you add heat to something that's already hot, it doesn't really increase the disorder that much, but adding the same heat to something really cold reshuffles a lot more molecular configurations here. So entropy will actually tell you this direction of the process. So systems will naturally tend to want to move towards higher entropy states. But here's the thing. We also know that systems also want to minimize energy. We want to go down to a lower energy state, right? So take a rubber band, for example. When you stretch the rubber band, it increases the entropy. There's multiple different mathematical configurations that I can stretch the rubber band in. But it also costs energy to stretch the rubber band. The rubber band won't just naturally just stretch. So essentially, we have these two drives, minimize energy and maximize entropy. And they can compete, right? So it'd be nice if we just had one number that actually captures the outcome of this and actually tells us which direction we are going in. And so that's where G comes in. And this is the Gibbs free energy. This is G equals H minus Ts, or at constant T, constant temperature, delta G equals delta H minus T delta S. So at constant temperature and pressure, change in Gibbs free energy will tell you whether a process will happen spontaneously, right? So suppose delta G is negative. So that would mean either delta H is negative, meaning we've lowered the overall energy of the system, which is good, or delta S is positive, meaning we've increased the entropy of the system, or both of them are true, you know? So if either or of those are true, then the reaction or the process is spontaneous. It'll happen if you just let it, if you give it a chance. It will just happen. Now, if I do delta G is greater than zero, it's the opposite. You need to actually do some work to make it happen. It won't just happen spontaneously because either you've increased the energy state by a large amount or you're decreasing the entropy. Or both. Maybe you're doing something where you're decreasing entropy and also lowering the energy state. Or increasing the energy state. Increasing the energy state and lowering the entropy. Sorry about that. So in that case, again, there's definitely an instance where you will have to do work to make it happen. And lastly, of course, delta G equals zero, you're at equilibrium. So systems balance, there's no net driving force in either direction. So let's actually do an example with Gibbs free energy here. And this is more going to be a conceptual example here. Have you ever used like an instant ice pack? So instant ice pack, which drastically lowers the temperature, right? Basically, how this instant ice pack works is you dissolve ammonium nitrate, which is NH4NO3. So you dissolve ammonium nitrate in water. So you do this from solid to aqueous. And this reaction, of course, is very endothermic. So it requires a lot of heat, which is why it gets very, very cold. So in this case, our delta H is positive. It's greater than 0, meaning the system absorbs heat from the surroundings and gets cold. Now, from the energy standpoint alone, obviously it looks unfavorable. It's not just going to happen. But if you've ever used an instant cold pack, you know that it actually does work. And that's because there's also a dramatic increase in entropy. We're taking a solid crystal and you're breaking it apart into ions moving in solution. So actually, this equation would probably be better written as NH4 plus aqueous plus NO3 2 minus aqueous. And so you have these ions moving in around solution compared to a solid crystal. So in this case, the entropy increase is also pretty large and positive. Now at room temperature, when we actually compute the delta H, which is, or delta G, sorry, which is delta H minus T delta S at room temperature, what we find out is that the delta G overall is less than 0 because the entropy term here is dominating so much that it's able to overcome the delta H term or the positive delta H. So even though it is an endothermic reaction and energetically it's not preferable to increase the energy of the system or the energy state of the system, because the entropy increase is so much more of a driving force, it's a stronger driving force than the enthalpy here, then the process becomes spontaneous. And that's how you get these instant cold packs that will just automatically happen, where you'll automatically get these crystals dissolve and move forward. And that's it. So all four of these terms, U, H, S, G, all of these terms are important thermodynamics concepts that we'll be coming back to and back to throughout your thermodynamics journey. So having a good understanding of what these actually are is going to help, especially when we start talking about thermodynamic cycles and as well as the diagrams, PV and TS diagrams, which we'll talk about in tomorrow's video probably. So I will see you there in the next one.